Every time you type a web address, your device faces a simple problem. People remember names like learn.knowddi.com, but networks deliver traffic to numerical IP addresses. The domain name system, or DNS, connects those two worlds. In this lesson, we will follow one DNS lookup from the moment you press enter to the moment your browser knows where to connect. DNS is often called the Internet's phone book. That comparison is useful, but incomplete. DNS is a globally distributed, hierarchical database. No single server stores every domain name. Instead, responsibility is delegated in layers. The root at the top-level domains such as .com beneath it, and authoritative name servers for individual domains. This structure lets DNS scale across billions of devices and names. Suppose your browser needs learn.knowddi.com. The browser and operating system first check their local caches. If there is no fresh answer, a small client called a Stub resolver sends the question to a recursive resolver. That resolver may be operated by your company, internet provider, or a public DNS service. Its job is to do the searching for you and return one final answer. The recursive resolver checks its own cache. On a true cache miss, it begins an iterative journey through the DNS hierarchy. First, it asks a root name server where to find learn.knowddi.com. The root does not usually return the website's IP address. Instead, it returns a referral to the name servers responsible for the .com top-level domain. Think of it as a trusted signpost. Next, the resolver asks a .com top-level domain server. The .com server does not manage the records inside KnowDDI.com, but it does know which name servers are authoritative for that domain. It returns NS records that identify those servers. When necessary, the referral also includes glue records, IP addresses, that help the resolver reach the authoritative server without creating a circular lookup. Now the resolver asks the authoritative name server for learn.knowddi.com. This is the source of truth controlled by the domain owner or DNS provider. It may return an A record for an IPv4 address, an AAAA record for IPv6, or a CNAME record that points to another name. Other record types have different jobs. MX routes email, TXT carries text metadata, and NS describes delegation. If an alias is returned, the resolver follows it until it reaches the address the client needs. The answer includes a time to live, or TTL. The TTL tells resolvers how long they may cache the result. If the value is 300 seconds, the resolver can reuse that answer for 5 minutes instead of repeating the full journey. Caching makes DNS fast and reduces load on upstream servers. A TTL is not a universal propagation timer. It is an expiration rule for each cache. After it expires, the resolver asks again and refreshes what it knows. The recursive resolver returns the final IP address to the Stub resolver, which passes it to the browser. DNS has answered the question, where is this service? The browser can now open a connection to that address, usually negotiate TLS for HTTPS, and request the actual web content. DNS helps locate the destination. It does not carry the web page itself. Traditional DNS queries use port 53, most often with UDP. Larger or truncated responses can retry over TCP. Newer options such as DNS over HTTPS and DNS over TLS encrypt the path between a client and its resolver. DNSSEC solves a different problem. It can prove that signed DNS data is authentic and unchanged. It does not hide the query. Encryption protects privacy. DNSSEC protects integrity. So the complete path is client, recursive resolver, root, top-level domain, authoritative server, and back again. Caches may shorten that path at several points. When DNS fails, check the record, the delegation, the authoritative server, and the cache, rather than treating the system as one black box. Once you understand the journey, DNS becomes much easier to design, operate, and troubleshoot.